What are GANs and how do they work? Generative Adversarial Networks, or GANs, are a powerful type of neural network used for unsupervised machine learning. Made up of two competing models which run in competition with one another, GANs are able to capture and copy variations within a dataset. They're great for image manipulation and generation, but they can also be deployed for tasks like understanding risk and recovery in healthcare and pharmacology. GANs are actually pretty new. They were first introduced by Ian Goodfellow in 2014. Goodfellow developed them to tackle some of the issues with similar neural networks, including the Boltzmann machine and autoencoders. Both the Boltzmann machine and autoencoders use the Markov decision chain, which has a pretty high computational cost. This efficiency gives engineers significant gains, which you need if you're working at the cutting edge of artificial intelligence. Let's take a look at how GANs work in a bit more detail. Let's start with a simple analogy. You have a painting, say the Mona Lisa, and we have a master forger who wants to create a duplicate painting. The forger does this by learning how the original painter, Leonardo da Vinci, produced the painting. Meanwhile, you have an investigator trying to capture the forger and second-guess the rules the forger is learning. Let's map this onto the architecture of a GAN. The forger is the generator network, which learns the distribution of classes, while the investigator is the discriminator network, which is learning the boundaries between those classes, the formal shape of the dataset. As we've seen, GANs offer some really exciting opportunities in artificial intelligence. There are two key advantages you need to remember. GANs solve the problem of generating data when you don't have enough to begin with, and they require no human supervision. This is crucial when you think about the cutting edge of artificial intelligence, both in terms of efficiency of running the models and the real-world data we want to use, which could be poor quality or have privacy or confidentiality issues as much as healthcare data does.
In the first block, these are the libraries imported in the code. Further, if you go down, we can see the generative model we have used. So here's the generative model. So is for discriminative. Now if we go to this part, here's the data. This class retrieves data from the local file. The discriminative and generative models are synchronized with each other so as to produce a resultant image. Right now the code is set to 150 epochs and the batch size is of 4 images. Now we are going to run the code and wait for it. Discriminative functions. Generative function consists of 15 hidden layers, and what it does, it produces an image and tries to replicate it with according to the original image, which is compared using the discriminative model, which consists of 10 hidden layers. What the discriminative model does is it compares the image of generative from generative and the original image. This process is going to take a lot of time. So we have already produced a trained model beforehand. Now let's check out the trained model. It consists of 20 fruit images and 4 face images for keeping the variety. The trained images, let's look at one of them in middle, 50th epoch. So this is the type of image which is getting printed. Now if we go to the 100th epoch, here the images you can see are getting better and better. Now if we go to somewhere near to 150th epoch, you can see now the images are far better than before.